Hello, this is our ECE 598 presentation. So it's on the characterization of 2D second harmonic generation microscopy images of pancreatic cancer. This is for me and Jordan, who's sitting next to me. So to start off, I'm going to give a brief overview of our presentation. I'm going to introduce pancreatic ductal adenocarcinoma. We're going to talk about second harmonic generation microscopy because that's what our data set consists of for images. Talk about some related work of other deep learning on second harmonic generation microscopy images. Talk about our specific data set. Talk about a method that we use called the wavelet transform modulus maxima, which is like a real-world biofit-based method we use for classification to compare to our deep learning method. And then we have a single image model, an 8-image model, and then our results and conclusion. So pancreatic ductal adenocarcinoma is the most common pancreatic neoplasm. When I say that, that's just any sort of tumorous growth or growth in the body. It's very deadly. Less than 10% of patients survive 5 years. And part of that is due to the difficulty of diagnosing early. So on the left, I have what's commonly used to screen for pancreatic cancer. And even as a layman, it's very hard to tell anything that is going on. So I have like the common bile duct labeled and pancreatic duct labeled and kind of where the mass is labeled. But if it's not in the head of the pancreas, it's very hard to see. It's not an organ you want to do surgery on because it's a head with a sac of fluid. And if you puncture that, you're dead. And it's a very important organ for the sugar and insulin production. And so it's kind of dangerous that we don't have a good method of detecting it early. And some of the plots that I've used in some of my thesis work is from the cancer fact, like the government cancer facts. You can just straight up see from these cancer facts that in pancreatic cancer, the rate of new cases and the death rate is like directly correlated. There's barely any difference. If you're diagnosed with pancreatic cancer, you're pretty much guaranteed to pass away. It's hard to treat. Chemoimmunotherapy are pretty much not effective on this cancer because it's already a giant mass by the time we can diagnose it. And on the right, I have an example of a female breast cancer, which has really good early diagnostics nowadays through a mammography screening. And we can see that over the past 2 decades, we're starting to improve reduce our death rate and improve our diagnostics rate, which when these curves diverge is really what you want to see because you're not only diagnosing earlier, but your more diagnoses aren't leading to more deaths. You're actually decreasing the death rate. So kind of like our hypothesis and some of our work is the answer just simply better diagnostics to improving pancreatic cancer survival, which our deep learning project is going to tie into.
So next, I'm going to talk about second harmonic generation imaging. This is the imaging modality that we use to gather our data set. So this is a nonlinear optical technique, and it is intrinsic and label-free, which means that you don't need any fluorophores, and therefore any sample preparation is so minimum that there's really no destructive of your sample before you image it. And specifically, this works on non-centrosymmetric structures such as collagen. Other examples could include myosin in your muscles. And it also allows you to deeply penetrate structures, so you can get into the 400 to 500 micron range before you really start having trouble, where typical like 1 photon techniques, you just don't have this deeply penetration of structures. So as you can see on the right, we have an SHG active and an SHG inactive, and that just goes back to what actually non-centrosymmetric means. And then furthermore, we have a collagen fiber, and you have 2 photons that hit at the same time, and it produces a single one, which is the SHG signal that we receive into our photomultiplier tube to create the image. So there are some related works. So the majority of the papers that use SHG images for machine learning are more centered on cancer diagnosis, but there are some others, such as ones that do segmentation of collagen. So the 2 closest related papers both use pre-trained convolutional neural networks. So one uses a VGG16 and the other one uses an AlexNet. The thing about using a pre-trained CNN is that you're kind of stuck with the input size of whatever that CNN has. So in this case, for both VGG16 and AlexNet, that's 224 by 224 by 3. And SHG images are grayscale, which means it only has 1 channel. So you basically duplicate the SHG grayscale image a few times to get those 3 channels per image to mimic the RGB input that these neural networks require. And then one of them is for ovarian cancer, so that's the VGG16, and the other is for classifying the 5 stages of liver fibrosis, which is the AlexNet. And in our literature search, we did not find any papers that use deep learning for PDAC classification. The closest one was using an automated intensity-based registration of Brightfield and SHG, but that was more with using like ImageJ and MATLAB, not necessarily with deep learning. And so what we think the field could benefit from our models is typically SHG images are captured 512 by 512 pixels. And with the inputs to what they had, they needed to downsize to 224 by 224, which loses some resolution. So we don't actually require downsizing in our model that we'll talk about in a little bit. And ours can work with grayscale images, so you don't have to duplicate into 3 channels to try to mimic that RGB. And then, like I said before, there's no previous model available for PDAC classification using deep learning. And this is our data set. So we have 40 PDAC patients that we got biopsy slides from Maine Health Institute for Research. So we had 20 labeled as cancer and 20 labeled as normal and healthy. Each image, like I said before, is 512 by 512 pixels and is taken with a 16-bit depth. We took 8 images or regions in each of the slides, and that indicates that we have 160 images per class for 320 images total. So you can see on the right here that we have a H&E stain slide, and you can see the cancer is outlined in red by pathologist, the normal adjacent is outlined in green, and then you have the fibrosis in yellow. And then we can see zoomed in representative images towards the bottom, where you can see the cellular features in the H&E slide, and then we have our representative SHG collagen slide there on the right, which is that darker image.
So people had questions about this when I presented in class, so I'm putting this here as it's not really what our deep learning project's about, so I'm kind of going to go faster than normal, but please ask questions. But I think this visualization will help some of you who are asking about it in class. So we're going to use the first derivative of a Gaussian wavelet. So I'm showing a Gaussian wavelet here just for our eyes, but we're actually going to use the first derivative of the Gaussian wavelet. But with the way I'm showing it, it actually works out that we are just using the Gaussian wavelet, but that's not how we do it in the program. And we're going to convolve with the image at different size scales. So here I'm showing a couple of different size scales where we know the resolution of our image, so we can say that, oh, the wavelet is going this many pixels, this many microns. So we're going to change the size of the wavelet, convolve it with the image, and then take the gradient of the image. So that's like the derivative, some calculus 3 we're pulling back from. And we're going to look at these maxima chains, which is where that pixel intensity is changing greatest. So that's where why we need to take the gradient. This white box is where we're going to zoom into, because it's not the maxima chains directly that we care about. It's the angle the maxima chains are at. So the words for this is modulus, which is the length, the intensity of the pixel change, and then the argument, which is the angle that maxima point is at on the maxima change. So we're actually going to look at these angles and use these to develop an analysis technique. So we're going to take all these angles and we're going to normalize them. Instead of an angle histogram, we're going to take that angle histogram and normalize it to have an area of 1, which is known as a probability density function. And it's important we do this so we can compare image to image. So one image that has 100 fibers versus an image that has 1,000 fibers. The histogram peaks in the 1,000 fibers is going to be greater, so if we don't normalize, we're going to see differences. So we normalize, we're going to compare to this 1/2 pi line, which is like assuming equal probability, there's no preferential angle. So if we take the area between the 1/2 pi line and the lines from our images, which I'm showing the PDFs from the images on the slide before, we can see that we can calculate an anisotropy factor, and that's going to change throughout scale. And these scaling relationships are very interesting, and it's part of the analysis technique, which I'll get into on the slide where we actually show the graphs. But we're going to look at like large scale anisotropy factors and small scale anisotropy factors to do our diagnosis on these images. And the equation for the anisotropy factor in mathematical form is on the bottom.
So to begin our model, we did some data augmentation. So we had the 16-bit depth size, and that's 65,535 values. So we rescaled it by that to make it to 0 to 1 instead of 0 to 65,535. We also allowed a rotation range of 90 degrees, a zoom range of 0.2, and then we used a fill mode of constant value of 0 for when we did the rotation, which is black, which is the background of our SHG images. We had the shuffle is true for training and false for validation, and that's because of the confusion matrix. And then one key thing is that all patient images stayed together. We didn't want it learning the differences. If you put some patients in the training and some patients in the validation, we felt that that might skew and provide false results for our model. And then the validation data is not augmented, it's only scaled by that bit size. And the reason we did all this data augmentation is we do only have a little over 300 images, which is a relatively small data set for a convolutional neural network. So we really wanted to give our model the kind of the best chance it had to learn the difference between cancerous and healthy. So we had two different models. The first is a single image model. So how we split it up was we had 192 training images. So we had 12 cancer and 12 healthy patients. We had 64 validation images for 4 of each category, and then 64 testing images, 4 of each category. And we can see our model representation on the right here. So we took each image, which is a 512 by 512. We did a convolution 2D, and then followed by max pooling, some more convolutional layers. And at the end, we finally did a global average pooling and a dense layer of 1 to use the binary cross entropy loss function. And we also used the atom optimizer with a learning rate of 0.001 with 10 patients and a new learning rate of 95% of old when that 10 patients runs out. And we did have a relatively small model of 58,117 total trainable parameters. And that's mainly due to the overfitting problems we would get with such a small data set. And these are the training and validation accuracies and the training and validation loss. So you can see accuracy on the left and loss on the right. Our best model was at approximately epoch 60. So you can see that it really begins to learn around epoch 200. It starts to level off to get accuracies for training around 85%, and then for validation around like 78, 79%. And then similar kind of trend over here with the loss, we do see it starting to really learn around epoch 200 with about 0.35 for the training loss, and then about 0.5 for our validation loss.
The 8-image model was just the idea if we took all the information from that patient at once, since we care at a patient at a slide level, not necessarily individual image level, if we were going to use this to assist the pathologist. And so we just took the single image model, and since we had 8 images per patient, we took 8 single image models. So we took our input as 512 by 8, which was an interesting problem to solve since the data transfers only allow 3, 1, and 5 channel inputs. I think 4 and 2 as well, but not 8. So we had to design our own kind of way to input a 512 by 512 by 8 instead of just using like the Keras flow from directory. So we took that, we split it into each image goes into its own training in this 8 split. So each image is getting trained on a single image model in the same order. So it's always the first image, the second image, the third, etc. And then that gets concatenated. And there's some dense layers that try to learn that concatenation to then make the final binary classification of cancer or healthy. And again, we have the same splits. We did run the random again, so they're not the same patients in validation as the single image model, but so it's the same like 4, 4, 4, 4, 12, 12 organization. And we had the learning rate at 90% instead of 95%, and that's because overfitting is even a bigger problem here because we're doing it at a patient level. We have even less inputs. We don't have 320. We only have the number of patients we have, which is 40 for our inputs in the data set. So we really can't have a really high learning rate for a long time. Otherwise, it'll just overfit. And as you can see, we did run into overfitting as a big problem with this model. So we can see our training validation accuracy hit 100% around epoch 300. and that the best model is at epoch 330, but I don't actually, you'll see from our data set, this doesn't actually seem to be the best model. It says it's at the overfitting point. And if you look at the graph, you can see that the training loss is already plateaued and the validation loss is plateaued. It just so happened to dip far enough, whereas a model, probably one of the models from closer to the 290 range would be a better model to use, which when we can run this again with our Google Colab, we'll be able to see if we can get a better model. So here are some of our results for the training. And you can see that again, overfitting occurred in the 8-image model, and that the single image model doesn't seem to be overfitting on the training, and it's doing way better than random chance.
And then, so these are for our validation for both the single and 8-image model. So we can see that overall for the precision and recall F1 score for our single image, we're in the high to mid 80s, and then even higher in our 8-image model for the validation. And then the testing is where it takes an interesting turn. So for the single image model, the testing did actually fairly well, fairly replicable with the validation. However, with the 8-image model, it was more classifying everything really as cancerous. And we really believe that that's probably due to just the sheer amount of data that it has to learn from, and also what Josh was saying too with the overfitting problem at the end there.
So this is the published technique. This part is published in the thesis, not in the paper, but the large scale on the x-axis is referring to large scale anisotropy factor. The small scale on the y-axis is the small scale anisotropy factor from what I was talking about before, and the green is a healthy slide, and the red is the cancer slide. So this is the same data used in the deep learning model, and that blue line is just pointing out where you can visually see clustering of the two groups. So we used k-means with two clusters, so algorithmically taking apart the two data sets. And with this, we got 90% sensitivity and 75% specificity for cancer. Those values are from the cancer calculation as the positive. And this only worked on a slide level, so it was like the average across all 8 images. It didn't really work on the individual image level because of variations in the anisotropy factor in one image. And this is the comparison. So we can see that the 8-image model didn't really work out very well, whereas the WTMM is an 8-image model and it's working out fairly well. So the single image model had better sensitivity, and which is kind of the more important metric where you want to make sure you catch everything that is cancer. And then the WTMM had better specificity. So if you handed it healthy, it would do better at correctly categorizing it as healthy. But again, it's more important to catch all the cancer without classifying everything as cancer like the 8-image model was. So the single image model can achieve a recall of 80 to 84%, and the 8-image model can achieve recall of over 88% in the training and validation data sets, but only 50% during testing. And there was not enough patients for an effective 8-layer model, though it seems promising that it will work if there is slightly more data or some more tuning of the hyperparameters, and that the individual image classification seems feasible, which was not replicable with like the current biophysics-based analysis approach.
So for the future work would be potentially to just gather more data for better training, especially with the 8-image model. We only have those 40 slides that we got. So that would require gathering more slides from Maine Health Research Institute. And then I did try to do a few shot approach. However, I was trying to use an OmniGlot data set, which has inputs of 105 by 105. So when you downsize the SHG images that are 512 by 512, I basically predicted everything as cancerous, similar kind of, I guess, to the 8-image model here. So potentially getting a better few shot approach to be working for this, to just because we don't have a huge data set could be beneficial, and an additional model to add to these two that we have working. Some image pre-processing would be beneficial as well. So these images weren't all captured on the same day. So there are some slight variations between day to day of the laser fluctuations, or sometimes some were taken a little brighter, some were a little darker. So maybe just some image pre-processing to kind of mitigate those differences. So it actually looks at strictly just the collagen structure, not the other stuff that is kind of in the image as well. And then this could potentially be translated to other SHG images. So we do have a breast cancer data set that we've acquired from biopsy slides, also from Maine Health. So to see if this model would be applicable to other cancer types as well would actually be a pretty cool and interesting thing to look into. So with that, these are all our references, and thank you guys for your attention. We would be more than happy to take any questions that you guys have.
Thank you.